Hello guys, welcome to this new video. So now we're going to work through the November 23 HL paper 1. I'm going to try and work through it like it were under exam conditions and guide you through my thought process, and we are going to skip the questions that are no longer required for the new 2025 syllabus. So in the first question, we're given that a resistive force acts on an object through a fluid given it with a speed v, and we're given this equation where k is a constant, and we need to determine the units of k. So in these questions, we usually want to write down the units of everything in SI units and see what k has to be, so the left side and the right side have the same units. So we know F is equal to m times a, where mass is in kilograms, acceleration is in meters per second squared, and we know that v is just meters per second. So we need to see what k has to be so that this equation is going to work. So that's the units of k over meters per second, and then we see that we need to put a kilogram per second over here so that the left and the right will have the same units. So that will be option D. In the next question, we're told that a graph shows the variation of the acceleration with time of an object moving in a straight line, which graph shows the variation of the velocity of the object with time t. Well, what we need to notice here is that in a velocity time graph, the slope is the acceleration, or the gradient. Gradient is acceleration. So we see that xa is always positive. So we need to look for a graph that shows us that the slope is always positive. So there are two options here, A or B. But at the start, here we have a local maximum. So that means that we need to have a maximum velocity, a maximum slope here. And then after that, it must continue decreasing. So here we're constantly increasing acceleration. We reach this maximum point in the middle. That's where we have this maximum over here. And then afterwards our acceleration starts decreasing again. The slope always gets less and less steep. So A has that property. According to B, our acceleration would be constant, as the slope of this line is a constant, so then the acceleration would look something like this. But that is clearly not the case here. So the answer is A. Here we're shown that a projectile is moving in an air with this path. What is the direction of the net force at the point shown? So here we need to consider what forces act on this object. And one of them we know is going to be gravity. So we can, if we would draw a free body diagram, we would have to draw mg. And well, we see that this path isn't really what we're used to. Usually we see some like symmetrical parabola like this, but here we don't. This also shows us that this particle was launched from the right, as here there is air resistance. So that's why the shape is a little bit funny here. We have air resistance, and what we need to know about air resistance is that it always acts opposite to the direction of our velocity. So if it was launched from the left to the right like this, over here we can see that it's dropping a little bit quicker because of air resistance. Then we know that the velocity at this point is going to be pointing this way, which means that our drag force is going to be pointing in the exact opposite to our velocity, as that's like friction always pointing opposite to which way our object is moving. So these are our two forces here, and if we want to find the net force, then we have to add these vectors up. So maybe this drag force is a little bit smaller, but if we would do like a tail to tip method to add up the vectors, then we would find that the answer is B. We would just have to slide this vector into the endpoint of this vector and connect the starting and ending point, something like this. That's why maybe the drag force is a bit smaller, but that's not of importance here. It's just the general direction we need to figure out. But it's clearly not going to be D, as that's not possible, so yes. So here we're given a diagram where two blocks of mass m and big M are on a frictionless surface. A force F is applied onto the block of mass m and causes the blocks to move with an acceleration. So there's some acceleration, and we need to select what is the force that the block of mass m is exerting on block of mass m, small m. So we know that the net force is going to be the acceleration times our total mass, like this. So our acceleration is just F over m plus m. This isn't really necessary for this question, as if the whole system is moving with an acceleration at a, it means that all components of the system are also moving with an acceleration a. So if we know that this block m is moving with an acceleration a, and it has a mass of m, then the force pushing this big block is just a times big M. So that's the force pushing here, and well, we need to decide what the force that the block of mass m is exerting on block of mass small m. So we need this opposite force, but due to Newton's third law, these two forces are equal and opposite, so this is also going to be just a times big M. So that's option B. So this can be simply solved with Newton's third law, that there's an equal and opposite reaction force. And since the whole system is moving with an acceleration a, the big block is also moving with an acceleration a. Then in question 5, we're told that the diagram shows a block of mass m sliding at constant speed on this incline. We're also given this angle theta. We have some coefficient of dynamic friction, and we need to state the magnitude of the normal reaction force on the block. Well, I mean, so n is the normal force, and we need to state what the angle is if we're sliding at constant speed. So this is the key thing we need to notice here. We are sliding at constant speed, so the net forces will cancel each other out, they will balance. So usually when we have some problem like this with a slope, we want to come up with a new coordinate system, because usually we work in the coordinate system that is like this, y and x, but that's not really beneficial to us here, as none of the forces really match up with this direction. The normal force is this way, like the frictional force, and there's also a slope this way, so it would make sense if we make a new coordinate system that is parallel with the slope. So if we do that, then we can write down every force in that new coordinate system. So our mg, I'll just sketch in this coordinate system here. So this will be the vertical side, and this will be the horizontal axis. And so we need to split up every force into components of this coordinate system. So if we consider some trigonometry, we will see that this angle here is also theta. Due to similar triangles, we have two sides that are perpendicular to each other. So this axis is perpendicular to this line, and this mg is perpendicular to this line. So the angle in between them is going to be the same. This is just like a property from math, so that's going to also be theta. And so we can see that we can write this mgx, this component in the horizontal direction, like for the slope, is going to be mgx will just be mg sine theta, as this is the side opposite to the angle. And then we can also write down that the vertical component will be mgy, for example, the y component, and this will be mg cosine theta, as this is the side that's adjacent to the angle. So now we know, just to summarize, that mgx, the horizontal component, will be mg sine theta, and our normal force is just the force acting on the block, on the contact with the incline. And well, we know that our block isn't moving like in this direction compared to the slope, it's only moving downwards. So that means that there's no net force in this vertical direction, which means that the forces must balance out in that direction. And if we see, we only have these two forces, the normal force and the y component of the gravity. So we will see that the normal force is just the same as the y component of gravity, which is mg cosine theta. And then there's still one force missing from our diagram, which is the frictional force. And we see that this is parallel to one of our axes, which is why we came up with this coordinate system. And we also know how to calculate this frictional force. It's just the coefficient times coefficient of friction times the normal force. And we know we're constant speed, so the forces in all directions must balance each other out. So if we look at this horizontal axis, the forces must cancel each other out. And well, the only two forces we have here are the frictional force and the x component of the weight force. So if these two cancel each other out, we will not accelerate down the slope. And well, now we just need to plug in our values. So this is mg sine theta. And if we rearrange for theta, we see that the sine of theta is mu n over mg. And then we just need to take the arc sine, the inverse sine of this, and we will see that this matches with option D. So yeah, this is quite a lengthy problem, but it's worth understanding this, as this also comes up in like the open-ended style questions, so it's worth spending some time to understand this. All right, so now we're told that an object falls from rest, so that means that the initial speed is 0 in vacuum. R is the rate of change of kinetic energy with time, so that's like delta E kinetic over delta time. How does R vary with T? So here we need to try and come up with some relationship between kinetic energy and time. So the first thing that might come to mind is this formula, 1/2 mv squared. This is kinetic energy, but this doesn't really have T in it, so we don't know how that varies yet. But if we do some smart substitutions, then we can get this function in terms of T, so that we see the kinetic energy as a function of time. And how we can achieve that is by replacing this velocity with some function of time. And well, what equation can we use that relates velocity, acceleration, and time? Well, if we look in our data booklet, we'll see that there's a very nice equation that does this. V is equal to the initial speed plus acceleration times time. We know that the initial speed is 0, so our velocity as a function of time is just acceleration times time. And well, our acceleration is going to be constant here, but that's also not so important here. But so now we can plug this in for V, so we'll have that 1/2 m times at squared. We can expand that out, so that's 1/2 m a squared t squared, like this. So, and we want to see the rate of change of this with time. So if we want to see delta E kinetic over delta time, as this is what R is technically, R is the rate of change with time. So what we need to do is just divide this newly obtained formula with T. So 1/2 m a squared t squared over T, and we'll find that it's like this. Now this is not the complete correct way to solve it, although it will give you the answer. It will give you that the R is proportional to just T, as this 1/2 ma squared is just a constant that can be thought of as like the slope of this line, and we just have a linear relationship here, so the answer will be A. But perhaps a more professional way to solve this would be to take the derivative of the kinetic energy with respect to time. So if you've already learned this in maths, we can take the derivative of kinetic energy with respect to time. And if we do that, we will have this equation. If we just look here, T is our variable, these are all constants. So you can also think of this like some constant times x squared, where x is just T, is our variable here. So if we take the derivative of that, it will just be 2 times the constant times x. So it's going to be 2 times this the 1/2 cancels out, and then we're just left with T here. And then here as well, we see that we are going to be left with a relationship which is linear with time. So this is perhaps a better approach, but it's not expected of us to know derivatives, integrals, and stuff like this in IB physics. It's a non-calculus course. So my first approach would probably be the expected way of IB to solve this. All right. So now X has a mass that is twice the mass of Y. The kinetic energy of X is 4 times that of Y. What is the value of momentum of X divided by the momentum of Y? Well, we need to get some equation that connects mass, momentum, and energy. And in our data booklet, we will find one that does just this, which will be p squared over 2m. And we are interested about momentum. So it will be beneficial to rearrange this for momentum, like this. And we're also told that the mass of X is twice the mass of Y. So what we can come up with is this relationship that if we multiply, since mass of Y is smaller, we need to multiply by 2 to get the same mass as X, and the same with kinetic energy. So the kinetic energy of X is larger, so if we multiply the kinetic energy of Y by 4, we will get the kinetic energy of X. And what we're interested in is the momentum of X divided by the momentum of Y. So this will be just the energy of X times 2 times the mass of X divided by square root energy of Y times 2 times the mass of Y. And well, we can plug in our ratio relationships that we just came up with. So we can replace all of the mx's, the x components, with the y components. So we can just plug in 4 for the energy, and then 2 for the mass. Here we don't need to write the 2 technically, and the EY and the MY, as those are both present on the top and on the bottom, so we could just cancel them out. So it's faster if we just write the numbers here now, and then the mass is twice that. And on the bottom we are just left with 1, as that's already EY and MY. And then this is root 8, which if we can also write as 4 times 2, and 4 is just 2 squared, so this is just the square root of 2 squared times root 2, and that's just 2 times root 2. So C. And then this next question, we are told that energy is supplied at a constant rate. So what that means is constant power. This is going to be important. So constant rate just means constant power to a fixed mass of a substance, so mass is also constant. The graph shows the variation of temperature of the substance with time. And we need to see which statement of the substance is correct about the substance. So here we see a regular temperature time graph. Here we are increasing the temperatures of our substance. Here we are changing the phase of our substance. So at the start here, we are likely in some solid phase. Then here we are in liquid phase, and then here we are in gas phase. And so here we go from solid to liquid, and here we go from liquid to gas. And when we go from liquid to gas, we call that vaporization. And when we go from solid to liquid, we call that fusion, like this. So it's important to know these terms, to be familiar with them, as the questions expect us to know this. And then we need to see which statement is correct. So the first statement says that the specific latent heat of vaporization is larger than the specific heat of fusion. Well, we know that we can use this equation, Q is equal to M times L. So this is the energy needed to change the phase of some mass M substance. And here we see that, well, we also know that power is just energy over time. And the power is constant. This is constant. But when we were vaporizing it, we needed to apply this constant power for a longer time. So this required more energy when we're comparing it to the fusion part, as that took got finished pretty quickly. We didn't need so much energy. We didn't need to apply our constant power for so long. So we needed more energy here, which means if we need more energy for the same mass of substance, then our specific latent heat of vaporization must be larger than our specific latent heat of fusion. As then we need for the same mass larger energy. That's only possible with a larger L. So that's why the answer is going to be A, but we can still discuss why the others are incorrect. So, well, there will be just as the exact opposite, so that's clearly not correct. And then they also tell us that the specific heat capacity of the solid is larger than the specific heat capacity of the liquid. Well, how could we approach this? Well, we know that there's this equation, Q is equal to mc delta T, right? Where delta T is the change in temperature. But we have power here, so if we just divide everything by time, then we will still have a correct equation. It's just that now we will see that we can rewrite it like this. And we know this is constant, as our power is constant. And if we look very closely, we have delta T here, or temperature, and we have time here. So if we look at this term here, we might notice that this is actually the slope of our graph. Slope of graph. As it's just the change in y over the change in x. That's the slope. And well, then we can see that the product of mass times c, where mass is also a constant, so the product of m times c times the slope is a constant value. So it means that if we have a large slope, then it follows that m times c must be small, and also vice versa, as that's how their product will remain the same. So we know that the larger slope will correspond to a smaller specific heat capacity, as m is also a constant, so actually only c is changing here when the slope is changing. And so we will see that the slope here for the solid phase is, for example, much steeper than the slope over here. So we can say that the specific heat for the solid phase is smaller than for the liquid phase. So that's why C is incorrect. Here it says the opposite. So it says solid is larger than liquid, but now we know it's an inverse relationship. So larger slope means smaller specific heat capacity. And then the last part says specific heat capacity of the vapor is larger than the specific heat capacity of the liquid. Again, that is incorrect, as our slope here is larger than over here. So our specific heat should be smaller for both of these. That's how it would be correct. All right, question 9. So for a fixed mass of an ideal gas, the pressure is proportional to, well, we can look at this equation, PV is equal to nRT. And well, if you only write this down, you might just immediately circle D and move on, which would unfortunately cost you a mark, as we have something here as well, something else as well. As we can see that it also mentions density, and whenever density comes into play, we need to watch out a bit, as density is mass over volume, like this. So if we rearrange this red equation for the pressure, we will find that this is nRT over V, like this. And if we rearrange this for V, we will find that V is the mass over the density. So if we plug this in to here, we will find that the pressure is nRT divided by m over p. So dividing by a fraction is the same as multiplying by its reciprocal. So we can just swap them like this. And well, what we will see here is that, well, n and r are just constants, so not so important. But we in fact, and also m is constant, it says in the question. So we see that the pressure is indeed proportional to the temperature and the density. So that's why the answer is going to be B, like this. So it's important to always remember that density can change a couple things, not only in this question, but there are also other questions where the consideration of density is crucial. All right, so here we need to say what the ratio of the number of atoms in 20 grams of neon over the number of atoms in 40 grams of krypton is. So the first thing I would notice here is that this 80 means that 1 mole is equal to 80 grams. And here 1 mole is equal to 20 grams of neon and krypton respectively. So, but here we have 20 grams already. So here we have 1 mole of neon, but here we only have 40 grams. So here we only have half a mole of neon. So we could convert moles to number of atoms, but we know that 1 mole is 6 times 10 to the 23 particles. And well, if we would multiply by this number on the top and on the bottom, we wouldn't get very far, as they will just cancel each other out. So our final answer would just be this fraction, which is just 2. So C. So in this question, we're told that a wave is traveling on a string. The graph shows the variation of the displacement of the string with distance and the variation of displacement of the particle with time, and we need to calculate the speed of the wave. Well, for speed, we need the wavelength and the period, or the wavelength and the frequency, but here it is going to be easier, as it's easier to tell the period here just from the graphs. So this graph is just like a picture of the wave. It's like we look at the wave from the side and we just take a picture. So we see that the wavelength here is 4 meters, as that is the distance between two crests or two troughs or just 2 points in phase. For example, this would also work. And then the displacement time just shows us the period here. So the period will just be the difference in time between 2 points in phase. So like this and this, or this and this, that will just be 2 seconds. So lambda is 4, t is 2, so our speed is 2. It's just the ratio of these. So 4 over 2. All right. Well, this question is about polarization. We can skip this. No longer needed. Here we have a question about Snell's law. So we're told that a wave is traveling from medium 1 to medium 2. Medium 1 has a refractive index of n1. Medium 2 has n2. The wavelength in medium 1 is lambda 1. Medium 2 is lambda 2. What is correct for the comparison of these two quantities? Well, so I usually like to start by drawing in this normal, as the angles are always measured in between the ray and this normal. So if we look at what Snell's law tells us, we will see that the sine of theta 1 or the sine of theta 2 is just n2 over n1. Here we can see that the theta 2, so the angle in the second material, is smaller than in the first material. So this means that in this fraction, the denominator is larger. That also means that so the angle in the second material is smaller than in the first material. This angle is clearly smaller than this. So yeah, if our denominator is smaller here, it must also mean that our denominator is smaller here as well. So we can say that n1 must be smaller than n2. And simply that's how the equation works. So we can already see it's either going to be C or D. And then we need to use this other relationship where n1 over n2 is v2 over v1. So the speeds of the waves. And well, we can rewrite the speed in terms of the wavelength. As you know, speed is just frequency times lambda, and frequency times lambda here as well. And we know frequency is independent of the medium. Independent of medium. The frequency only depends on the source that's emitting this wave. So the frequencies we can cancel out. And so we see that n1 over n2 is equal to lambda 2 over lambda 1. And well, we can simply use this relationship, as we know that n1 is smaller than n2. So the top here is going to be smaller than the bottom, and with the same consideration, then V2 must be smaller, lambda 2 must be smaller than lambda 1, as the top on both sides should be smaller than the bottom, so yes. So here, we're given that the first harmonic for standing sound wave is established in a tube, one end open, one end closed. The length of the tube is increased by 10 centimeters. The next harmonic is formed. What is the wavelength? All right, so let's see what's happening here. So in the first harmonic, we have a length of L, and it always looks something like this. This is a fourth of the wave. So we can say that the length, this whole length, corresponds to a fourth of the wavelength. And then the next situation is going to be when we make it a little bit longer. Then we're going to have the next harmonic. And well, we kind of just have to know what these harmonics look like in these three situations. One of them is one end open, one end closed. Another situation is when both ends are open, and another situation is when both ends are closed. So I suggest knowing what these look like for like at least the first three harmonics, as usually only these come up. Maybe the fourth one as well, but nothing more. So here, L plus 0.1 is just going to be 3/4 of the wavelength, like this, as 3/4 of the wave are present in here. So, well, we know that L is lambda over 4. So if we plug this in, plus 0.1, go to 3/4 lambda. We can subtract lambda over 4. So we'll have lambda over 2 here. And so lambda is 0.2. So C. Question 15. 2-point charges plus Q and minus Q are placed a fixed distance apart. Where is the electric field strength equal to 0? Well, electric field strength is a vector quantity, so it also has a direction. And what we need to know is that electric field always shows the direction a positive particle would move. So if we were to place a positive particle over here, due to this negative charge, it will get attracted, as opposite charges attract each other, but due to this plus 4Q is going to get repelled, as like charges repel. And the magnitude of the force is proportional to the distance and the charges, as F is just K big Q small q over r squared. So the further away we are, the weaker this force is going to be, but at the same time, the larger the charges, the stronger the force is going to be. So we kind of have to see what is going on here. So like if we look at point A, one of the electric fields will point this way, and the other one is going to be larger and point this way due to the plus 4 charge. So that's not possible, as we want 0 net electric field, so we would need to add these two up, and they would have to be approximately the same size and pointing in opposite directions. And well, point B is going to be the same situation as point A. It's also not possible. At point C, both electric fields point towards the minus charge Q, as this repels it and this attracts it, so it's also not possible. So it must be D. As well here, the plus 4Q repels it and the minus Q attracts it, and it's closer to the minus Q, but minus Q is a smaller charge, so it's going to have approximately the same size as this larger charge, but a longer distance. So yes. Okay, a cylinder of copper with diameter D and a length L has a resistance R. What is the resistance of a copper cylinder with diameter 2D and length 2L? Well, for this we're just going to need to use this formula, where we know that A is pi r squared, and well, we can also rewrite this in another form, where is d squared pi over 4 is also the area of a circle, as the diameter is just, the radius is just diameter over 2, so these two are the same. So we see if we double the diameter, the area also doubles. So the resistivity stays constant as we still have the same copper cylinder. So if we double the length and double the diameter, then the area will be times 4, so it's going to be 2 over 4, so a half. So the resistance will half. We can just plug in how everything changes and then see what the net change will be. Alright, and then question 17. So 3 particles with identical magnitude of charge but different mass is shown as they enter a region of uniform magnetic field. Same initial velocity. Magnetic field is into the plane of the paper, and we need to say the mass of particle X and the sign of the particle. So I think it's easier to see what the sign is first of all, as if we use our right hand rule, we will see that the sign must be negative, as if we place our thumb in the direction of the velocity, our pointing finger in the direction of the magnetic field, then our middle finger will point in the direction of the force. So if we do this here, the force points in the opposite way, but if it's an electron, then it would point this way. As if we use the right hand rule, we assume we're working with a positive charge, but if it's a negative charge, then it's just the other way. And then we can do this at any given point. It will always point towards the center of this circle, so yes. And then the mass. Well, we know that there's a force acting here, which is only the magnetic force, and this is acting towards the middle of this path circle, so it's also the centripetal force. And we know that the centripetal force is mv squared over r, and the magnetic force is qvb for a point charge. So all we need to do is rearrange this for the mass. So it's going to be qb over v, as the v's, one of the v's cancel out. So we see if we have a larger radius, we must also have a larger mass, as they have the same initial velocity, same magnetic field, same charge. Not the same charge, but the same magnitude of charge. And yes, so the mass must be larger as our radius of motion is also larger. So B. We have another ratio question. So here we're going to need to use the formula G is equal to Gm over R squared. And here we are told that the mass of planet X is 300 times larger than the mass of Earth. So mx is equal to 300 times the mass of Earth. And the radius is 10 times the radius of Earth. So Rx is equal to 10 Re. So we need to compare the gravitational field strength on the surface of planet X in terms of the gravitational field strength on the surface of Earth. Well, Gx will just be G times mx over Rx squared, and then we can plug these in terms of the radius of the Earth and the mass of Earth. So that will just be 300 me over 10 squared Re. So that's going to be 300 over 100. So that's going to be 3 times G times me over Re squared, also squared, like this. So it's going to be 3 times that of Earth, like this. Now we're given a sample of artificial element of sebargoium, and it's created with 4 times 10 to the 22 atoms. We're given the half-life, and we want to see how many atoms remain after 1 minute. So half-life just gives the time to half the number of atoms. So in 1 minute, that's 60 seconds. So that's going to be 4 half-lives. And well, after every half-life, the number of atoms half. So after the first one, we'll have a half, then another half. It will half again, then it will half again. So that's 1 over 16. So the remaining atoms will be 1/16 of that. So we need to multiply this by 1 over 16. So 4 over 16 times 10 to the 22. and 0.25 times 10 to the 22, and well, that's the same as 2.5 times 10 to the 21. So that's A. So this is also in the old syllabus. We don't need to know any more of these exchange particles and mesons and so on. And then the next question, we need to say which of the following is not considered to be an ideal, to be a greenhouse gas. So, well, we just have to kind of remember that, well, oxygen is not a greenhouse gas. The other three are. And 22. So we're given a black body with temperature T as a peak wavelength of lambda. What is the peak wavelength when the temperature increases by 33%? So we need to know this relationship. It's in the data booklet. Lambda max is just this constant divided by the temperature. So our new T will be 33% larger. So that's the same as 4/3 times the initial T. And we want to see how the maximum wavelength changes. So again, we can just plug this new T into this formula. So T is going to be 4/3 times the T. So we can bring this to the top. It's going to be like 3/4 times 2.9 times 10 to the minus 3 over T. So it's going to be, and this is the original lambda, so 3/4 times the initial lambda. So B. Alright, then this next question. It's executing simple harmonic oscillations with total energy E, amplitude x naught. What is the kinetic energy of the particle when the displacement from equilibrium position is x naught over 2? Well, in our formula booklet, we're given two equations relating to this. One of them is that the E total is this. And our potential is this. So, and we need to find kinetic energy. Well, we know that the total energy is constant. This is just equal to E potential plus E kinetic. The sum of the two types of energies we have, and that's a constant here. So if we subtract E potential from this, we will find the E kinetic. So E kinetic will just be 1/2 m omega squared times x0 squared minus x squared, as we can just factor out this part when we do the subtraction. And we need to see when it's half of the maximum amplitude away from the equilibrium position. So if we see this over here, the equilibrium position we can just say is 1, and then we subtract a half of this as we're half of this entire distance. So there's going to be 1 minus 1/4, so that's 3/4. So yes, so our answer is going to be C. That's going to be our kinetic energy. As we could also write just x0 here, x0 here, and then we will just be left with x0 here, like this, or x0 squared to be precise. And then the rest remains the same. And yes, and E was the total energy. So we see total energy is just this, but then there's an extra 3/4 multiplier, so that's why answer is going to be C. Here we're given a interference intensity pattern from 4 slits. What change occurs when the number of slits is increased, but the separation of the slits and the width of the slits does not change? So if the separation of the slits doesn't change, then the positions of the maximum won't change. So that's something we can just remember. And if we increase the slits, we're going to have sharper maximum. So if before we had something like this, then if we increase it by a lot, so if we make a lot more slits, these will become a lot sharper, something like this. So the width of the primary maxima is going to decrease as it went from this distance to something smaller. So the width decreases, the position doesn't the position does not change as the separation of the slits remains the same. Number of secondary maxima decreases, that's also not correct. And well, the intensity will also not really change here, as it's technically modulated by a single slit diffraction pattern, so that cannot change either. Then, well, this question is also from the old syllabus. We don't need diffraction gratings anymore. And then this question is about the Doppler effect. So a siren emits a sound of wavelength lambda and a C when it's at rest. The siren now moves towards a stationary observer at speed v. What is the wavelength and the speed of sound received by the observer when v is much less than c? Well, we can already see that the speed is just going to be the same, as the speed only depends on the medium we are traveling in, not the speed, especially when the speeds are so small. It's not going to change the speed of light. So that is simply, the speed of sound, sorry. It only depends on the medium we are in, so like whether in air, glass, water, so on, nothing else. And then we need to see how the wavelength changes. Well, we're going to need to see what formula we can use from the data booklet. And well, here we have a moving source, so we're going to need to use this, as it says in the data booklet. Like this. And well, we have to kind of decide for ourselves whether this is a plus or a minus, but this can be decided rather simply, I think, because we know that the siren is moving towards us, so the observed frequency must be larger. As the waves are getting more compressed, the wavelength is becoming smaller and smaller, so the frequency must increase. And the way the initial frequency can increase is if this number is larger than 1. And well, the only way this can be larger than 1 is if this is a minus sign over here, because then the numerator will be larger than the denominator. As from v, we subtract some positive number, so the top will be larger, so we'll have a fraction that's larger than 1. So that's why we know we're going to need to use a minus sign. And well, here the speed of the sound is c and our speed of the source is v, so a little bit different symbols, but that's no problem. And we also know that the frequency is just the speed divided by the wavelength. And speed is just wavelength times frequency. So if we replace these frequencies with these terms of wavelengths, we'll see that c over the new wavelength is just c over the old wavelength times c over c minus v. And well, the c's here will cancel out. And we can also take the reciprocal of both sides so that we get rid of these fractions. So, or we could just multiply across with this and this so that we already have a good equation. So then we will find that lambda is equal to lambda dash times c over c minus v. Again, here I just cross multiplied technically, and that's how I got this equation. And then we need to find the equation for lambda prime, or this lambda dash. So we just have to divide by this, which is same as multiplying by the reciprocal. So that's going to be c minus v over c. This is going to be lambda, the new lambda, and well, this is just c over c minus v over c, and this is lambda times 1 minus v over c. So that is option B. And yes, this was quite a lengthy question, quite a long calculation needed. Well, this one's going to be a little bit easier, luckily. Here we're given that an isolated point charge Q is located at point X. Two other points Y and Z are such that the YZ is equal to 2 times XY. So if we label this distance X, then this distance will be double that distance, so 2x. That's what this means here. And we need to state the electric field at Y and Z. Well, how could we do this? We know that the electric field is just K times Q over R squared. So it changes with the distance. The charges are the same here. The point charge is the same. And well, what's important to see here is that we have some distance x here, but the distance is measured from here to here and from here to here. And from x to z, the distance is 3 times. Okay, well, sorry, I think I made a mistake here, because this is not what the problem told us. The problem told us that the distance of xy times 2 is the same as the distance from y to z. So actually what it told us was that this is twice the length of x to y. So this is 2x. And so this, if this is x, then q to z is going to be 3x, as that is x plus 2x, like this. And so we triple the distance. And so we need to see how the electric field changes when we triple the distance. So if we say that at y we had an electric field of 1, then at z we'll have some other field strength, 1 over 3 squared. As we can just plug in this ratio here. So this is just going to be 1 over 9, which is just 9, which makes sense as y is closer to x, so we expect a larger electric field at y. So we could already eliminate a and b, but we need to remember that the electric field varies with the distance squared, and that's why it's not going to be 3. It's going to be 3 squared. All right. Now we are told that two very long parallel plates, x and y, have equal and opposite charges. The potential on x is Vx and the potential on y is Vy. Okay. And Vx is larger than Vy. Point particle of positive charge q and mass m is held at rest midway between the plates. So there is no small q here. And the particle is released. And we need to state which plate the particle will move toward and what kinetic energy will it have. Well, if Vx is larger than Vy, then we know that the electric field lines will point this way, as these electric field lines always point in the direction that the electric field is decreasing. So like this. So I mean the way the potential is decreasing technically. Also, if we think on Earth, if like this is Earth, the field lines always point downwards like this. G points downwards as it's pointing from a higher potential to a lower potential. That's kind of similar here as well. So we know that it's going to move towards plate Y, as these lines always show us the direction a positive point charge would move. And well, here we have a positive charge, so that's the direction it will move. Now we just need to see the kinetic energy. Well, we know that the work when moving a charge between a potential difference is given by this formula. So the charge times the change in potential. But since we are halfway here, if this whole distance would have a delta V, then the delta V here would just be Vx minus Vy. But since we're only moving halfway in between, the potential between this point and this point is only half of this. So the potential difference here is just going to be Vx minus Vy over 2. So that's going to be our potential difference. And well, we just need to plug this in. So potential difference is Vx minus Vy divided by 2. So that's D. So we need to divide by 2 because we are midway. All right, then this question: a hollow metallic sphere of radius r has a positive charge q. So positive q. P is a distance. P is a point distance r over 2, distance from the center of the sphere. What is the electric potential and the electric field at point P? Well, the electric field we can already say is 0. So this again is something you just have to remember, because the explanation, the derivation for why the electric field inside a charged metal sphere is 0 is beyond the syllabus. So there isn't really any tool we can use to understand this. That's why it's simply required to remember this fact, as IB can ask this. So just remember that the electric field is zero everywhere inside this field. It's kind of because like the electric fields cancel out in every direction, and that's why. So the net field will just be zero, as there are positive charges all around the circumference, and they all exert an electric force, and they all cancel each other out. And then we know also that the electric field, or maybe it's better to write it like this, so the change in potential is minus, right, so in the data book it's like this. So E is equal to minus delta V over delta R. So the change of potential with distance. So if we go some distance, we have to see what distance we went and how much the potential changed, and that will be the electric field. But here we see that it doesn't change. So delta V is just 0, because, well, E is 0 inside the sphere. As we have just discussed, the electric field is 0. So this also means that delta V is also 0. So that means there's no change in potential as we move around in the sphere. And well, if we think about what the potential at the surface is of the sphere, or like the inner surface of the sphere, that's going to be the same as everywhere else in the sphere, as it doesn't change with the radius. And well, the potential at the surface can be found using this formula. It's also in the data booklet. And since there is no change of potential within the sphere, this is going to be constant. So this will also be the potential at point P, as it's constant everywhere in the sphere. Here we are told that a satellite of mass m is in orbit around a planet of radius r and the mass m. The total energy of the satellite is minus gmm over 4r. All right, so what is the radius of the orbit? So here we need to come up with a relationship for the total energy of the satellite. So we know, this is in the data booklet, that the potential energy is minus gmm over small r. And well, we know that the kinetic energy of an object is 1/2 mv squared. But this isn't too useful for us, as we want it in some form like this, so that we can sum these two energies, so we can find the total energy. But as you see, there's no velocity here, so we somehow need to replace this velocity. And well, luckily we have a formula for orbital velocity. So when the satellite is orbiting, that speed is just the square root of gm over r. So if we plug that in there, we find that the kinetic energy is just 1/2 gmm over r. And the total energy is just E potential plus E kinetic. But this is a negative, so we're going to need to subtract it. So this will be 1/2 gmm over r minus gmm over small r. And if we subtract these two, we will find that it's 1/2 gmm over r minus, obviously, but we already know that the total energy is this expression, so we can write this here. And the question is what the radius of the orbit is. So the question is, what does this radius have to be over here, such that the total energy is this formula here. And well, you see, if we plug in 2r here, then we will find this formula, as this 2 will multiply with this 4, and then we will be left with this minus 1/4 gmm over r. So the radius must be 2r for the relationship to be correct. Yes, this question is also in the old syllabus, so no need anymore. And then here we are told that a conducting ring is dropped from rest above the ground. As it falls, the ring passes through a region of uniform horizontal magnetic field. Air resistance is negligible. All right, and then what is correct about the acceleration A of the ring as it enters and as it leaves the region of magnetic field? Well, this can be derived with a very well, not very lengthy. I'll show you how to do this, like how to do this properly, but probably in a paper one, you don't want to spend this much time thinking about every situation. You just want to remember Lenz's law, which means that, which pretty much just says if something changes, the induced current and the EMF will be in such a way to counteract this change. So it wants, this is like due to also the conservation of energy, but pretty much we can think of it as it enters the loop, as it enters the magnetic field. Due to Lenz's law, the induced EMF will be in such a way to try and keep it out of the electric field, as it wants to return to its original state. So the force will be upwards, meaning as it enters, the acceleration will be smaller than g, as we will have a force upwards and we'll have gravity. And if it was only gravity, it would be A, but we have a force also upwards, so the net force will be smaller than g. And then as the ring leaves, we can consider this in the same way. It's already in the magnetic field, so it wants to stay in there. And then when it starts dropping out, there will be an upwards force again, which will try and keep it inside the magnetic field. And so the net force will again be in such a way that the acceleration will be smaller than g. As again, we'll have gravity downwards as well on the loop. And like this, the net force will be still pointing downwards, but a little bit smaller than g. So yes, that's how you would do it properly. And then if you would want to derive this with the right hand rules, then you would need to consider the direction the current is induced when it lands, when it falls into the loop, into the magnetic field. So when it falls down, the current would be this way. And then with your another right hand rule, you can see that if the current is moving to the right, then there must be a force upwards in the magnetic field. And then when it's dropping out, you can do this similar idea and come up with the same result. So this question 33 is also the old syllabus. This one as well, it's about capacitors, this one as well, and this one is not. So this question 36 is about the photoelectric effect. So here we're told that light falls on a metallic surface whose threshold frequency is f0. The number of photons incident per second is constant, which graph correctly shows how the current I emitted from the surface depends on the frequency of the incident light. So threshold frequency is kind of just the minimum frequency a photon must have in order to emit an electron from the metallic surface. And it's also important to note that the intensity, the current here, so the current is the rate of change, the rate of flow of charge. So how much charge is emitted per second. And this is only dependent on the number of photons that are incident on the surface. So if we have more photons incident, then the photons will be hitting more electrons, so more electrons are being emitted, so the current increases. But here we're told that the number of photons incident is constant, so the current being obtained from this cannot change, or it cannot be increasing with the increasing frequency. So B and D are incorrect. But below the threshold frequency, there cannot be any electrons emitted, as then the photons don't have enough energy to emit an electron, as that's the definition of the threshold frequency. So it must be A. As before, there are no electrons emitted, and then afterwards some constant number is emitted. Even if we increase the energy, that doesn't matter. The number of electrons emitted will still remain the same. In question 37. So here we're told in the Bohr model of a hydrogen atom, we need to determine the angular momentum of the first excited state and the ground state. So if we have some nucleus here, this is usually considered the ground state, the first energy level, then the second energy level, and so on. And in the data booklet, we have this very nice equation, which states that mvr, the angular momentum, is equal to nh over 2 pi, where n is the level. So the angular momentum only depends on which energy level we are on. So in the first excited states, we are n equals 2. In the ground state, we are n equals 1. So at the second level, the angular momentum will be 2 times as much as on the first level. So that's option C. Then question 38 is also from the old syllabus. So 2 questions to go. So in 39, we're told that in rate of decay, the energy of the emitted beta particles is continuous. This is explained by the existence of the neutrino. So again, the explanation of this is quite lengthy and also not necessary to know. I just recommend you to remember this, that since beta decay has a continuous spectrum, it shows that there's a neutrino. It has to do with things like there are free particles being present in this reaction, and the beta particle, the antineutrino can carry away different amounts of energies depending on how the particles collide, as the momentum and kinetic energy must always be conserved, but it's much easier if you just remember this. You're never really going to have to explain this, but it does come up quite often to just simply state that this shows that neutrinos exist, or at least it shows that there must be a third particle, and then they determine that the third particle should be called a neutrino. And then the last question, so it's about the Rutherford scattering and deviations from the Rutherford scattering. So we need to decide what deviations show for the Rutherford scattering. And well, this again is something that you kind of have to just know. There are deviations because when this is the nucleus, and when we shoot alpha particles at it, if they come really close, they usually would just pass like right next to it or pass through small deflections, as only the electromagnetic force is being used here. So it's small deflections, but at very specific energies and at very specific places, there's very large deflection angles. So like even 180 degrees backwards, they just get like completely repelled, and that's because of the strong force, which has a very small range, really only the range of the nucleus. But if the alpha particles come really close, the strong force also starts acting on them, which repels them much stronger. So the first one is correct, as that's kind of why we have these deviations. And it also allows for an estimation of the radius of the nucleus, as if we know how much energy we had to shoot the alpha particle at to achieve this deviation, then we can calculate the distance of closest approach, and therefore the nucleus radius as well. And well, the third one is incorrect because, well, the alpha particles must have a really high energy to overcome the repulsive force of the electromagnetic force in between the nucleus and the alpha particle. As if they don't have enough energy, the distance of closest approach will be very far away. Therefore, they need a high energy to be able to come this close to the nucleus. Therefore, this is at high energies. And well, so this was the November 2023 paper 1. I hope I was able to help with some of the questions, and see you in the next video.